Hello, calculus class. Today we're going to start looking at power or Maclaurin series, uh, finding those for functions where we're using a list of kind of known expansions that we want to memorize. So this is instead of doing them directly from the Taylor or Maclaurin series definition and trying to compute the derivatives and recognize a pattern. It's kind of more of knowing a basic library of series expansions and modifying or manipulating that library to suit your individual function that you're attempting to model. So let's have a look at our library. I think the one in our book is pretty similar to this one. So you've got a bunch of different basic functions. You've got an exponential, you've got a couple of your basic trig functions, a logarithm, you've got the binomial general one with an infinite product on top that we've been using. And you've got the basic series expansion for those centered at 0, so the Maclaurin series expansion, written as a power series. So we're going to kind of memorize these. I think that's pretty easy to do. Don't think it's like a big task. It's going to be very simple to memorize them. And manipulating them should be a whole lot easier than trying to recognize the pattern each and every time. So cosine of the square root of x is the first example that I wanted us to look at today. So the cosine, you don't want to memorize the compacted series expression, I should say, the compacted power series. If you can write down the first 4 or 5 terms, usually it's really easy to compact it down to this. If not, I think you need to do some more practice. So let's try to write down the expansion first by writing out some terms for cosine of root x. So the first step in this process is to start writing down the cosine of x. Don't use your book to rely on. Try to start remembering what cosine of x looks like as soon as possible. So cosine of x is going to be 1 minus x squared over 2 factorial plus it, and sign always alternate. It's pretty easy to remember. If you remember one, you can remember them both. And minus x to the 6th over 6 factorial plus, we'll go one more term, x to the 8th over 8 factorial plus dot dot dot. So first I always try to write down the basic one from my memory. Then I'm going to plug in square root of x for all of the x spots in the series, and I'll be done. I'll just compact it down and be done. So I think this is a pretty simple problem. The cosine of square root of x, then, it doesn't get moved. There's no spot for it to plop in there. Square root of x squared is x. That's going to be over 2 factorial. I'm going to leave these as factorials because I want to eventually compact this back down. That's an issue that you need to continue to try to work with instead of always just resolving the factorial right away. A lot of the time it's good to leave it there so that you can see the pattern more simply. Sometimes you need to resolve it. It just depends on the problem. Here we're going to put square root of x in and raise it to the 4th. That's 1/2 to the 4th power, which is squared. I'm going to leave the factorial again, like I said. Let me get my pad out of the way. Then I put it here. And it's going to be x to the 3rd over 6 factorial. And you can keep trying to plug it in, or you can start to see if you recognize the new pattern. Obviously, this is increasing by powers of only 1. It's still alternating. So this is going to be 4th power, and these factorials are kind of maintaining the same pattern that they were before. So let's see if we can condense this down. I think we're going to be able to do that. Let's see. So we've got an alternator, so I'm going to put an alternator in, maybe -1 to the n. If I start at 0 and I go -1 to the n, that's going to be positive first, which is what I want. That's going to work. Okay. And then I think we've got a simple factorial on the bottom, or do we? Well, on top it looks like it's just going x to the n to me. X to the n. If you put 0 in, you don't have an x. You put 1 in, you get x. That's working out. And then on the bottom, it's skipping like kind of every other one. So if I put 0 in, I get 1 factorial. That's good. If I put 1 in, I get 1 factorial. That's not greatest. So we need this, that we can put this over 1 factorial just to clarify, right? So we need to go 1, and then 2, and then 4, and then 6. Maybe that 1 factorial isn't the best way to visualize this. Let's get rid of that. And think about this. Maybe this is 0 factorial. Oh yeah, because 0 factorial is 1, if you remember. That's an identity, which you could work out, but not in this video. So 0 factorial is 1. So this needs to be like 2n factorial, I think. If you put 0 in, you get 0. If you put 1 in, you get 2, and that'll give us this. If you put 2 in, you get 2 times 2 is 4, and it'll give us this. There we go. Oh, I forgot my infinity. There's the condensed version of this modified for the square root input power series. All right, let's look at another problem. I think this one was on your first quiz. So on your first quiz, I made this extra credit because we hadn't exactly done them this way. We were just doing them directly from the definition. So on your quiz, I think you had to recognize for e to the x what the power series was from the definition. I should say, what is the Maclaurin series expansion? So you're thinking like this, right? You're going like f of c, which if it's Maclaurin, it's going to be 0 plus f prime of 0 times x minus 0 squared over 2 factorial plus f double prime of 0. So this is what you did on your quiz, right? Then let's just not go x minus 0. So this is going to be not x squared. This is 1. This one's going to be x squared over 2 factorial. I messed up right there. So that's going to be 1 plus f triple prime of 0 times x cubed over 3 factorial, and so forth. So e to the x, luckily, is like the easiest function to do this with. If you put in 0, this is going to be 1. If you take its derivative, it's e to the x still. You put in 0, that's going to be 1 times x over 1. Plus, this is still going to be evaluated at 0. This is always going to be 1. I'm just going to stop writing it on the next steps. Times x squared over 2 factorial. Plus, then this is just going to be x cubed over 3 factorial. And the pattern is super simple to recognize here. You could even build that into its compacted form super simply by just going n factorial and x to the n. There we go. It's so easy to get e to the x. It's our most friendly function. That's why we've bothered to use the base e for our exponentials for the longest time. So what you might not have known how to do on the quiz is how to modify e to get this guy. You might have tried to take successive product rules with chain rules in them, and that would have been a pain. Certainly possible, but a pain. So now what you can do is you can just go, well, if I know e to the x, I can figure out e to the negative 2x by plugging the negative 2 in all of these spots. So that's going to be, let's get a different color going here. So that's going to still be 1 plus, oh, is it going to be plus now? I think not. I think it's going to be minus 2x. And then we're going to have plus, and negative will get squared, so this is going to be 4x squared over 2 factorial. And then minus to an odd is going to be negative 8x cubed over 3 factorial. And then it's going to be positive again, and you can probably see the pattern developing. I should have put a plus dot 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 there, over 4 factorial. So that's the idea. So before I compact this down, I think I'm starting to write sideways here. I want to do the final thing, which is, remember, we also had to multiply by this x. So I'm going to have x e to the negative 2x now. So that's just going to be this x times all of that stuff. So that's going to be x minus 2x squared plus 4x cubed over 2 factorial minus 8x to the 4th over 3 factorial, because it's not affecting the factorials or the coefficients. This is going to be 5th over 4 factorial. And hopefully that's enough for us to be able to see a pattern. You know what, let's write this pattern down here. So the final power series expansion that we want on this one, I think we'll probably just try to start with 0. Maybe we'll want to start with 1. Let's see. So can we put this over 1 factorial? 1 factorial is 1, and this over 0 factorial. That kind of clarifies. Okay, so I think we're just going to put n factorial on the bottom. That was easy. If we put 0 in, we don't want that. We want it to be 1. So maybe x, and it goes 1, 2, 3, 4, 5. Okay, so maybe it should be x to the n plus 1, I'm thinking. Yeah, because then we'll get x first, and then when it's 1, we'll get 2, and so forth. There we go. And then on top we have 1, 2, 4. It's also alternating, so I need an alternator. So I'm going to go negative 1 to the n, because I'll get positive first there. There we go. And now we have powers of 2 up here. So what do we have? We have times 2 to the n, is it? So that's going to be 1, which will be this 1. And then if I put n equals 1 in, I'll get 2. If I put n equals 2 in, 4, 3, 8, and so forth. I think that's it, ladies and gentlemen. I kind of have it scrunched in there. But you can see how easy it is to use these known expansions. Which I didn't even use one, I just rederived the expansion for e to the x. But you can, of course, go up to your table and just have that memorized right here. Here's that same expansion. Very easy to remember. Okay, let's look at a few more problems that involve a little bit more complicated versions of these kinds of ideas, but basically are still just going to involve remembering the expansion and modifying it. Here's another neat example. This time we'll do something involving an integral, so you can actually use these series in combination with integrals and derivatives. I don't think that should be a surprise since we've already been differentiating and integrating series. So let's look at integrating, finding an expression, I guess, for the integral of this function. So the base function is e to the x, so the first step would be, of course, to write down the known expression for e to the x, which is, I think, this, right? So we were just working with this a second ago, so I'll just write it out to about 4 or 5 terms. There we go. So then we're going to plug in negative x squared for all the x's. That's going to be 1 minus x squared here. Then when we put x squared in for this squared, negative x squared I should say, it's going to turn to positive x to the 4th. And yep, and then that's going to still be over 2 factorial, and then negative odd is going to be negative x to the squared cubed power to power multiply 6th over 3 factorial, and I think you can see the pattern is that it's alternating, so this is going to be 8th, 2, 4, 6, 8, and we're just going to maintain the same factorial expressions on the bottom. So there we go, we've got the integrand expressed as a power series. Now we need to integrate that. So we're going to integrate this whole thing with respect to x and see what we get. So if we integrate 1, we get x. If we integrate x squared, that's x cubed over 3, right? We integrate this, that's x to the 5th over 5. I'm just going to leave this 2 factorial in case I need it to figure out my pattern. And this is going to be negative x to the 7th over 7 times 3 factorial plus x to the 9th over 9 times 4 factorial plus dot dot dot. Okay, there we go. So now I think they want us to use this in this problem to actually estimate this integral. This is kind of like an integral from statistics. It's the integral that is for the normal distribution, or the z-curve in other words, is very, very similar to this. It's just got some extra yucky looking constants. It's basically an e to the negative x squared function, which by the way is an integral that we couldn't do with the techniques that we've learned so far this year. So let's go ahead and give this guy a shot now. So we know what the series is. So this integral is going to be, let me get my same color scheme going on. This integral is going to be what? So we're going to integrate from 0 to 1. We're going to integrate that function, which we've represented like this. So maybe we should just write down and resolve these factorials now, because there's no need to actually, well, I don't. Let's resolve the factorials and see what happens. Maybe we'll need them, maybe we won't. I'm not sure yet. 5 times 2 factorial is 10, and then we have, let's see. And you know what? I think I have a mistake here, because what didn't we already integrate up here? Yeah, we totally already integrated, so I don't need to put that there. Instead, what I want is to use the fundamental theorem on this guy and evaluate this guy from 0 to 1. Because remember, this is already the integrated expression for, maybe I should write that down up here, this is already the integral of e to the negative x squared. It's going to be that series. So we're going to evaluate that from 0 to 1. So this is the antiderivative already, I should have said. Alrighty, so a plus, that's not supposed to be a plus, let's fix that up. That is supposed to be a minus. So we're going to have minus x to the 7th over 7 times 3 factorial is 6. And we're going to have plus x to the 9th over 9 times 4 factorial is 24. If we want one more step, let's go one more step. So we'd have minus x to the 11th over 11 times 5 factorial is 120. That should give us a pretty good estimate. So now let's go ahead and evaluate that. So that's going to be, the zeros are going to totally go away, so we really just need to plug in the 1. So that's going to be 1 minus 1 cubed is 1. 1 to the 5th is 1. 1 to the 7th is 1. 1 to the 9th is 1. I now need my calculator. 9 times 24. I'm not going to bother you with the calculation here if you don't need it. That is 216. And 1 to the 11th is 1. 11 times 120 is 1320. So that's going to be it. So let's go plus dot dot dot. And then we're going to have really here, we're going to have a minus 0 for the 0 being put in all these guys. So there we go. So we've got that minus 0. Okay. So what do we have here really? Well, isn't this an alternating series? It's an alternating series. I think it's going 1 minus plus, minus, plus, minus. And so for that, if we want to do an estimate, and of course we can't do this exactly unless this actually converged to something specific, but since it's an alternating series, I think we can use the alternating series test remainder theorem. So we can use the alternating series remainder theorem here, which I think says that the series can be estimated by just looking at the very next term. So we could, of course, just add all these guys up and see what we get. And yeah, I mean, the error in the series, according to this theorem, says the error is going to be less than or equal to the very next term. So what is this? How many terms do we have here? 1, 2, 3, 4, 5, 6, 7. So the error, if we add up those first 7, will be less than the 8th term, which is equal to what? Wouldn't that be positive 1 over 13 times 720? What is that? 1 over 13 times 720. Let's pull up our calculator here. Clear this guy out. Oh, I don't want the graph. 13 times... Oh. 13 times 720. So 1 divided by that is going to be a pretty small error term. Oh yeah, so we're doing pretty good. What is that? 0.000106. So 0.000106. Our error is going to be less than that if we add up these guys. So let's just go ahead and add up these guys. So let's go back and grab our calculator and do it. So what do we have to add up there? Let's see. We can do it right here. Let's clear it out. So we're going to go 1 minus 1/3 plus 1/10 minus 1/42 plus 1/216 minus 1 divided by 1320. And there we go. So I got that our answer here is 0.746729. So 0.746729. How many of those digits can we really rely on? We'll go back over here and say, well, the alternating series test, since this was an alternating series, says that the remainder after 7 terms is going to be, it's going to have an error of less than 0.0001. So I think we can at least say these aren't real sure, 0.0001. So this digit might not be exactly accurate, but we can definitely trust these 3 digits right here. So there you go. We went back and looked at an estimate, and we also integrated one of these kinds of modifications of a power series. Let's look at doing some long division and some creative multiplication of these series in the next little segment. So here's the next example we're going to look at. And so we went over this one in class already this year, but I don't know if you'll have seen it already. So these are two other examples from our textbook. So using known expansions for e to the x and arctangent of x, you can find a product of functions like this. So we're going to take the e to the x expansion, which we already saw in the last couple examples, and then we're going to look at the arctangent of x Taylor series, or excuse me, Maclaurin power series expansion, which of course we could get from back up in our table right here. Do we have the arctangent in this one? Yes, we did. There it is. So you just pull that down, and the idea here is to multiply that by this one. So the only problem is here you're going to be multiplying an infinite number of terms by another infinite number of terms, and that can be difficult. So you can see the two expansions right here. What does it look like when you multiply one by the other? So the book has an interesting strategy for doing this infinite expansion. And I think it's really based on the same premise of what we've been doing since we started Taylor and Maclaurin series, and that is trying to do just enough terms in such a kind of expansion until you kind of recognize the pattern and can take it from there, and maybe even condense it down. We'll see if we can condense this one down, I'm not so sure. But anyway, here's the book's approach. It wrote down the e to the x expansion on top, and then it wrote down the arctangent of x expansion, keeping kind of place value in an accounting sort of way. So the x degree term, the first degree terms kind of line up, third degree terms kind of line up, fifth degree terms kind of line up, and so forth. Really, let's just put this one down here. So the fifth degree term for this should be 1/120th x to the fifth, right? Okay. And then you go about multiplying everything by everything because, right, this is multiplication, so I should be multiplying 1 times that and times that and times that. And that's what you're going to do here, except you're doing it in a very methodical way. Now, this is, of course, not the only way to do it, but I think the book's approach is interesting. A little hard to follow on your own, though. So we're going to take this x first, and we're going to multiply it by everything. First by 1, and we get x. Then by x, and we get x squared. Then by 1/2 x squared, and we'll get 1/2 x cubed. Then by 1/6 x cubed, and we'll get 1/6 x to the fourth. And finally by 1/24 x to the fourth, and we'll get 1/24 x to the fifth. Let's take it a little bit farther than the book and go times this one that I wrote in and say that's going to be 1/120 x to the sixth. Okay, so we're going to take this one more term than the book just to expand it a little more. Okay, and then it does the same thing, so I'm going to erase the green there and do the same thing with this next term. So let's erase this out of the way. And now we'll do the same thing with this guy. So now we're going to take this guy and multiply him by everything. Because remember, in this expansion, everything is supposed to get multiplied by everything. But if we start by looking at the smallest degree terms and see what ultimately is going to happen with all the smallest things, make sure we don't miss any of the smaller things, we'll be able to figure out the pattern. That's the idea. So now we're going to have this times 1, and that's how we get this. And then we're going to have this times x, which is going to be -1/3 x to the fourth. Then we're going to have this times this, which is going to be -1/6 x to the fifth. And then we're going to have this times this, which is going to be what? -1/18 x to the sixth. So we're going to have -1/18 x to the sixth. Like I said, we'll do ours a little bit further, and then you'd have to keep going. So this would be like -1, what is that? 24 times 3 is 60 plus 12, 1/72. X to the seventh would be right here, and so forth. Alright, so you'd want to keep, it's going to need to get multiplied by this, and then that term would be right here. So that's the idea. Let's erase this and then do it with one more step. And hopefully we'll be able to recognize a pattern at the bottom. I'm not sure, but we'll find out. Let's see, can I get a different color going? Oh, I don't have a lot of color choices. Maybe I'll go back to blue. There we go. Okay, so now we'll go this guy. We'll go this guy times 1, and that's this. We'll go this guy times x, and that's going to be 1/5 x to the sixth. And then we'd keep going in like fashion. If we needed to go further to recognize the patterns, this next thing would be 1/10 x to the 7th. And you know what, since we're at it, let's just go back and do one more thing for this. So I went to the 6th power, so let's go put one more term in here. Wouldn't this be plus 1 divided by 720? Let me double check. I sometimes forget my factorials. So 5 factorial is 120 times 6 is, yep, I'm right. So 1/720th x to the 6th. Let's go ahead and add one more term on here so we can get a little bit more accuracy in, if we need it for our pattern. So this would have, guys, you guys remember this was x times 1, this would have been plus 1/720th x to the 7th when we went this guy times this guy. Okay, now we've got it all the way to the 7th power, so let's go ahead and see what we have down here. So now we're just collecting like terms and seeing how much of each type of degree we have. Well, we have one of those, we just have one of the x squareds. We've got a half minus a third, which is a sixth of the x cubes. A sixth minus a third is a sixth of the x to the fourths. Here you're going to want to do a common denominator, so let's go ahead and pull up our calculator, shall we? Go ahead and grab our calculator over here. Hold on one moment. See what I've got on my calculator here. So right here we've got, let's see, can I fit it on this side? Yeah, I can. So I have what, 1/24th minus 1/6 plus 1/5, and what is that math? Fraction, that's 3/40. So you can see their 3/40 number there. Now we're going to continue ours a little further, so let's go ahead and do that. So we've got 1/120th, then we've got minus 1/18th, and then we've got plus 1/5. Turn that into a fraction for us. So that's 11/72. Let's get that in there. So we're going to have 11/72 x to the 6th. I think this one's going to be positive too, so we're going to have, you can see that this looks like some kind of interesting pattern. Well, maybe not. Let's see if it's positive. Pull up our calculator again, and we've got 1/720th minus 1/72 plus 1/10. Let's see what fraction that is. 7/80th. It was positive like I thought, though. So we have 7/80th x to the 7th, if I'm not mistaken. So there's our expansion. So over here we could, of course, write that this is e to the x times the inverse tangent of x. That's going to be equal to this expansion. I don't know if we can condense this down, though. This is a pretty weird pattern. Positive, 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 negative, positive, positive, positive. I'm guessing this one would be negative. So this would be an interesting, perhaps cubic alternator that we'd have to put on here. We've got 1/6, 1/6, and we've got like 40, 72, 80, 3, 1, 1, 3, 11, 7. This is a pretty complex pattern, so I'm not going to try to condense this one down. But there's a little more accuracy for you. Let's look at another one where we need to really keep track of terms and account them kind of in a precise fashion. So what if you wanted to figure out the expansion for tangent, just plain old tangent? Well, we have an expansion for sine that we should know. I think we just used this expansion for cosine a moment ago. So if we have one divided by the other because of our basic tangent identity, we can just do a long division on this to get. So let's see if we can follow the book's long division, maybe add a little bit more if we like, and so forth. So we've got sine of x that we want to divide by cosine. So the cosine stuff should be the thing we're dividing by, and the sine stuff should be the thing that we're putting in the dividend, or whatever. Okay, so there we go. Let me get those out of the way just so we don't get confused here. Alright, so now we just do long division. We say 1 times what will give me this x? Well, that's going to be x. And then you take this x and you distribute it back through. So that's going to be x right here. It's going to be negative 1/2 x cubed right here. It's going to be x times that is 1/24 x to the 5th, and so forth. So if let's just leave it at this. I think this is good enough. Okay, so then we've got that done. So then we go ahead and subtract here. So let's change colors. So we go 1/6. I always really like to write this minus. Students who don't write the minus in long division pretty much always mess it up. So make sure you're doing that. So 1 minus 1 is nothing. Negative 1/6 minus 1/2 is negative 1/6 plus 1/2, which is, I think, 1/3. Yes. And then we've got 1/20th minus 1/24th, 1/120th minus 1/24th. So I guess we'll just trust them. But that's going to be negative 1/30th. And then you repeat. So then you come over here and you say, okay, now I'm going to go 1 times what gives me this guy. Well, that's going to be this guy. And you take this and you multiply it back through. So we've got that times that is this. That times that is negative 1/6 x to the 5th. There we go. And you can see where this is going. So then down here you've got another minus that you've got to go negative 1/30th minus a negative 1/6. So it's going to be negative 1/30th plus 1/6. That's pretty easy to do without a calculator. Nice common denominator, right? So it's going to be 5 minus 1/30th, which is 4/30th, which is 2/15. And that's how this came about. And now we've kind of got the series expansion. I think that I can already see a pattern in this one. Let's try to write down the compacted version. What would be the next step? So it goes 1, 2, I'm guessing this would be 3 x to the 7th, and then down here that's like 3. This is like 3 times 5. I bet this is 3 times 5 times 7, and then I bet the next step would be like this. We'd have to carry this division out further down this way if we wanted to be sure, but that's the idea. And remember where this comes from, of course. It's coming from up here in the quotient. So I actually kind of tried to find the pattern for the results of this long division for the quotient here for quite a while, and it's actually not an elementary function, and the math you need is kind of beyond the scope of Calc 2, so I don't want to put that in this video. At least we might do that kind of thing later. But so we're just going to leave it like this. So I hope you found that so far creating power Maclaurin series expansions using that table of known expansions is actually a really easy process. Let's do one more where we need another identity. So we did this really simple tangent equals sine over cosine identity. Let's do one more. So let's say that we need to integrate, no, not integrate, let's just try to find a power series for the function, I don't know, cosine squared of x. Let's try to do cosine squared of x. So if you're going to do that, I think you need to remember a really important fundamental identity we've used this year for integration, which is if you wanted to integrate cosine squared of x, you would have to express it as 1 plus the cosine of double x over 2. Remember, that's how we integrated cosine squared and sine squared, is we used those double angle identities, and I'm not going to go through the derivation again here. But anyway, that's an identity you should be long familiar with. So basically, I think we can use that identity to take the basic expansion for cosine, which I think was 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Let's just go check. I haven't been doing very many of these problems. Yeah, that's right. And modify it to suit this cosine squared by going like this. So then we need, for our identity, we had cosine of double x for right there. So we're going to stick that in. So we're going to have 1 minus 2x squared is 2 quantity x squared is 4x squared. And then we have 2 quantity x to the 4th is 16x to the 4th. And if we put that here, we're going to have this. This is supposed to be a plus. Then minus 2 to the 6th power is 64 x to the 6th, right? Over 6 factorial, etc. So now we need to go and say, well, that's cosine of double x. Isn't this really 1/2 plus 1/2 of that? So now we need to have half of that and add a half to it. So that's what we're going to go down and say down here, that 1 plus cosine of double x over 2, which is really cosine squared of x in disguise, is 1/2 this 1/2 plus 1/2 of this stuff. So what's that going to be? Well, we're going to have half of 1 is half, plus a half is 1. And then this is just going to affect all the other terms. So we're going to have half of that is going to be minus 4 over 2 is 2. I'm going to leave my factorials for pattern recognition here in a moment. I think probably want to do it like that. Let's see. So we're going to have half of 16 is 8 x to the 4th over that 4 factorial. And then half of 64 is 32 x to the 6th over 6 factorial. Let's do one more term. Plus the next one would be 2 squared, 2 to the 4th, 2 to the 6th. This would be 2 to the 8th, which is, I think, 256. 256 over 2 would be 128. Is that right? 128? Yeah, 128 x to the 8th over, this is 6 factorial, this would have to be 8 factorial. So I think that's good enough to write this cosine squared of x in a condensed form, so we can say n equals 0 to infinity. I think on top we have powers of 2 that are alternating, so that's like x to the 2n. If I put 0 in, I get 1. If I put 1 in, I get 2. If I put 2 in, I get 4. There we go. That's working. I need an alternator, so -1. It's supposed to start positive. That should make that happen. And we've also got 2, 8, 32, 128. So we've got powers of 2. Is that going to be 2n plus 1, maybe? If I put 0 in, then the first term would be 2 to the 3rd. That's 8. No, I think that's not right. It's got to be the other way. Maybe -1. If I put 0 in now, it's going to be 2 to the -1. Oh, and that's going to be like negative. That's going to put a 2 down on the bottom. No, that's not right. Maybe it's supposed to be, let's see. So we need, for n equals 1, we want it to be just 2 to the 1. Okay, so then maybe this is just times, maybe not 2n, maybe it's just n plus 1. So when we put 0 in, we get 1. Oh, maybe it's just -1. I'm doing very bad with my guessing on this today, if you can tell. So I think this is going to be 2 to the n plus 2, maybe? No. It's going to be -1, maybe? Yeah. Let's see. I'm really having trouble with this guy. I don't know why. So when I put n equals, I guess I'm going to have to go brute force. So n equals 0, I just want it to be 2 to the 0. N equals 1, I want it to be 2 to the 1. N equals 2, I want it to be 2 to the 3rd. Let's see. N equals 3, I want it to be 2 to the, that's 3rd, that is 5th. Yeah, so I think we've got to have a space in here. This has got to be like 2n something. If I go 2n minus 1, and I put n equals 2n, I need to get 3. So that gives me 3, right? If I put 1 in, I get 2 times 1 is 2, minus 1 is 1. If I put 0 in, I got 2 times 0 minus 1 is... See, that's not going to work because then that's going to be 2 to the -1, which is 1/2. And we're going to have a 1/2 here on this first term, which is a problem. Let's come back to this. Maybe we can just take this 1 out of here totally. I think we probably want to do that. Yeah. So that's probably what we're going to do. If we go on the bottom, though, and we put... yeah, maybe we should just stick this off separately and just get rid of this 1. That's what I'm thinking right now. Because 2n minus 1 seems like the only way we're going to do this, or the only way I see we're going to do it. So then what kind of factorial do we have down here? I think we're definitely going to have a 2n factorial. So if we put 0 in right now, if we leave this alone, then we're going to have 0 factorial, which is 1. If we put 1 in, we'll have 2. If we put 2 in, we'll have 4. If we put 3 in, we'll have 6. So really, it's just this power of 2 that's kind of messed up. So, I think I'm going to have to fix this. Maybe I made a mistake that I didn't see, but you guys can see if you found that yourself. I think I'm just going to say 1 plus this series, and I think I'm just going to change things around a little bit. So I might have to fix things up. So I am going to say that this now starts at 1. And now when I put 1 in, I'll have that. If I put 2 in, I'll have that, etc. So then I'll put 1 in, I'll have that. If I put 2 in, I'll have that. If I put 1 in here, the first term will be 3 minus 1 is 2. So that's going to be 2 minus 1, which is 2 to the 1 power, which is exactly what I want. If I put n equals 2 in, then I'm going to get up there 2 to the 4 minus 1, which is 2 cubed, which is 8 like I want. Yes, that's going to be it. Let's see, is the alternator good? If I put 1 in, then I'm going to get negative, which is what I want. I think this is the way we needed to do it. So you can see on this problem that I actually had to take out that first term in order to make everything else work, because this was messing up just that one. Everything else was going with it. So that's also possible to do. So there's another example of using known series, manipulating them, doing a little bit of hard work at the end to figure out exactly how the expansion works. And hopefully I got it right. If I didn't, I'm sure you guys can tell me about it in class, because I am done making videos for this morning. I will see you next time. Hope you have fun with your Taylor and Maclaurin expansions.